All right, so let's start a new chapter. So today I'm going to talk about electromagnetic induction and Faraday's law. Okay, and it is chapter 21. Okay, so the first thing I'm going to tell you is the induced EMF. Okay, so in the last chapter, you see that when there is a current in a wire, then we can have the magnetic field. Okay, so the current carrying wire can give us magnetic field. Okay, so that means that we get magnetic field or magnetism from electricity. So here in this chapter, you will be seeing the opposite. The magnetic field or the magnetism can give you electricity. Okay, all right. So to understand this, let's go to a simulation and let's try to understand this situation. Okay. So here you see that we have a circuit. Okay, and this circuit is not connected to any battery or the potential difference. Okay, so I mean, as you know that the important component in a circuit is the voltage source or a battery, right? So here we don't have a battery. Okay, but even though we can have EMF here, okay, electromotive force here, or the voltage. Okay, so okay, let me put a voltmeter here that will tell us how much voltage is over there. Okay, but here you see instead of a battery you see a magnet. Okay, now the magnet is at rest, and you don't see any voltage here in the voltmeter. So you see that the value of the voltage is 0 or there is no current here. Okay, so if there is a current, you will see the glowing in the filament bulb. Okay, so that is normal, right? Now if I move this magnet, okay, then you will see there is some current, there is some voltage in this circuit. Okay, so let's see. So you see that, so you see that, right? So this tells us that if in this loop, so in this coil, there is a change in magnetic field. If there is change in magnetic field in this coil, there is some induced EMF here. Okay, the change in magnetic field in the coil basically induced some electromotive force or voltage in the circuit. Okay, all right. So you see that in last chapter we get magnetism from electricity. Here we see that we get electricity from magnetism, and the voltage or the EMF we get from the changing of the magnetic field is called the induced EMF. Okay, because it induced some electromotive force. Okay. Now this induced EMF depends on something. So I mean, this picture is basically the same thing as the simulation, so I'm not going to discuss it. Okay, so now let's look at these factors, okay, which affect the magnitude of the induced EMF. Okay, so the first thing that can affect the magnitude is the how quickly you are moving the magnet. Okay, if you are moving the magnet rapidly, the induced EMF will be large. Okay, so here you can see that. So if the speed is small, the voltage is small. Induced EMF voltage, induced EMF is also small. If it is quick, then the EMF is also large. Okay, another thing that affects the magnitude is the area of the circuit loop. Okay, higher the area, higher the induced EMF. Okay, all right. So here, few things to remember. Okay, so you see that change in the magnetic field can induced EMF in a circuit. Okay, and you can change the magnetic field two ways. Okay, so one way is just moving the um, uh, the magnet. Another way you can, here I cannot do it because this coil is fixed here in this simulation, but you can also move the coil towards the magnet while the magnet is at fixed. Okay, so if you move uh, the coil towards or away from the magnet, you are also changing the magnetic field in the coil. Okay, so that can also induce the magnetic field. Okay, so you can um, change the magnetic field in two way. One is by changing the or by moving the magnet towards or away from the coil, or moving the coil towards or away from the magnet. Okay, and the next thing is the area of the coil also affect the magnitude of the induced EMF. All right. Now, this situation is basically fast understand by Faraday, by two scientists. One is Faraday, another is Lenz. Okay. So now we are going to learn the expression, mathematical expression or algebraic expression of the Faraday's and Lenz's law. Okay. Before we do that, we have to understand something called magnetic flux. Okay. And magnetic flux is exactly equal to, exactly very similar to the electric flux. So if you remember, the electric flux was something like this. Phi E equal to electric field times the area times cosine theta. Okay. And magnetic flux is exactly the same thing. You have to just replace the electric field by magnetic field. Okay. So, and here you see that. Okay, all the factors are very similar. Okay, now if you remember, when you learn about the electric flux, we consider electric field lines. So here we have to consider magnetic field line and then an area. Okay, so let's say this is a area A, and you know that area's direction is perpendicular to it. So this is the area's direction. Okay, and this is the magnetic field's direction. So magnetic flux, for a uniform magnetic field, something like this, okay, that passing through a loop area, let's say the loop area is A, the magnetic flux is this. Okay, and here theta is the angle between the magnetic field lines and the direction of the area. Okay, direction of the area means here this one, okay, which is perpendicular to the area. Okay, so you see that in this case the theta is 0 degree. Okay, and cosine 0 degree is 1. Okay, so in this case our magnetic flux will be maximum, and that will be equal to B times A, the magnetic field times the area, because cosine theta is 1. Okay, and in this case you see that area and magnetic field are perpendicular to each other. That means theta is equal to 90 degree and cosine 90 degree is 0. So the flux in this case will be 0. Okay, so this is the maximum flux, this is the 0 flux, and in general it is B a cosine theta, very similar to electric flux. All right. Now, so here, the magnetic flux is analogous to the electric flux. It is, similar to the electric flux. Magnetic flux is also proportional to the total number of magnetic field lines passing through the loop that is perpendicular to the magnetic field line. Okay, what is the standard international unit? Standard international unit is Tesla meter square or Weber. Okay, 1 Weber is equal to 1 Tesla meter square. Okay, so how it comes? It comes from this equation. Okay, so B is Tesla and A is meter square. That's why 1 Weber, that is the standard international unit of magnetic flux, is equal to Tesla meter square. Okay, now you see that in magnetic flux we have both the magnetic field and area, okay, on which the induced EMF depends on. So here in the last slide, we learn about these two things. Okay, one is the how rapidly you change the magnetic field, and another is the area, right? And you see that magnetic flux contains both quantities. Okay, so now if you understand this, you are ready to understand the mathematical expression for Faraday's law, Faraday's and Lenz's law. Okay, so Faraday's law tells us that the induced EMF in a circuit is equal to the rate of change of the magnetic flux through the circuit. Okay, so if we have only one loop, then the Faraday's law is this. If we have n number of loop, n number of loops, then we have these. We have to just multiply these. So here this curly is the induced EMF, and delta phi b delta t is the rate of change of the magnetic flux. Okay, all right. And what is the minus sign? Minus sign gives the direction of the induced EMF. And this especially I mean this case, I mean the minus sign is basically understand by Lenz, and this part is called the Lenz's law. Okay, and what is the physical meaning of this minus sign? The physical meaning of the minus sign is this. Okay, so you know that when you change the magnetic field through a circuit, there will be a current, right? And you know that if there is a current in a wire, there will be magnetic field. Okay, so you see that from the magnetic field we get current, and from that current we get another magnetic field, right? Now we have two magnetic field. One is the original magnetic field, and one due to the induced current in the circuit. Now Lenz's law tells us the direction of these two magnetic field, the original magnetic field and the induced magnetic field, will be opposite. Okay, so here you can I think see this. So here you see that magnet is moving towards the circuit, and that's why we see the current in the emitter, or if you use the bulb, you will see the glowing in the bulb. Okay, and these red lines and blue lines basically tells us the field lines. Okay, so when the magnet is moving towards the circuit, okay, you also see the red and blue line from the circuit. Okay, that is basically tells you that there is a magnetic field due to the induced current. And you see that when the magnet moves towards the circuit, the circuit gives a, on the left hand side, the circuit gives a blue line. So you see now, okay, and blue means repel, right? So it means that there is a south pole on the left hand side. Okay, and you know that south and south repel each other. Okay, and when it is moving away from the circuit, there will be a red line. So you see that. Okay, and red line also try to oppose the motion of the magnet. Okay, so that's basically the Lenz's law. Lenz's law tells us that the magnetic field, original magnetic field, and the magnetic field produced by the induced current should be opposite of each other. Okay, all right. The next thing I'm going to talk is the EMF induced in a moving conductor. So it's basically the example. Okay, example how Faraday's law or Lenz's law works. Okay, and here while doing this, we are going to learn something called motional EMF. Okay, so we learn about induced EMF. So when we have something like this situation, we get basically something called motional EMF. Okay, and we are going to derive an expression for the motional EMF. Okay, so now let's consider this one, this picture and this picture are very similar. In the left hand side, we have the magnetic field. The cross line tells us that the magnetic field is into the screen, and the dotted line, uh, circle tells us that the magnetic field lines are out of the screen. Okay, otherwise it's basically similar. Okay, and here we have a conducting U-shaped wire and then another conducting rod. So this is a conducting rod. Okay, all right. Now here the area of a loop is this one. So this is the loop of area. So this is our loop. Okay, so this is the area. Okay, now if I move this conducting rod in this direction, the new area is now this. Okay, so the new area is now this. Right, so here you see that we don't change the magnetic field. In the last example or in simulation, we see that the magnetic field changes. So here you see that the loop changes, the area of the loop changes. So earlier it was the blue square or blue rectangle. Now it is the red rectangle. Okay, so the area changes by this amount, right? So area changes by this amount. Okay, so here we did not change the magnetic field. Here we change the here we change the area. Okay, and if I call this distance delta x, okay, so let's say this is delta x, and if you move this rod by a velocity v, okay, then we can from this equation we can write that delta x is equal to v delta t. Okay, and delta t, let's say delta t is the time by which you move this rod from here to this position. Okay, so the change in length here or the change in area will be, okay, change in area will be this length delta x and also this length. Okay, because we are talking about the area. So this is the this side and this is L. Okay, so the area will be, because it looks like a rectangle, so the change in area will be delta x times L, and delta x is equal to V delta T L. Okay, so this is the change in area. Now if I want to know what is the induced EMF here by changing the area, we can start from the Faraday's law. Okay, so let me write down here. So the Faraday's law tells us that induced EMF is equal to delta phi B delta T. Okay, so let's ignore the negative sign. I'm just interested on the magnitude here. And here you don't change the magnetic field, right? You change just the the area. So cosine, so here cosine 90 degree. Okay, so the direction of loop and the magnetic field are the same. Sorry, here it is 0 degree. Okay, so that's why cosine 0 degree and cosine 0 degree is 1. So let's ignore it, and that is this. Okay, now we don't change B. Okay, so we can take B out of this change equation. Okay, so B equal to delta A over delta T. Now delta A or the change in area is this V delta T L delta T. So delta T cancel out. So what we get is B V L. So this is the induced EMF here. And this EMF we get because we moved the conducting rod from this position to this position. Okay, and that's why this induced EMF we call the motional EMF. Okay, so in the next slide I discuss all the math. Okay, and this is called the motional EMF. Okay. Now, this motional EMF also produce an electric field. Now let's try to understand. And I need to, we want to understand what is the direction of the current in this case. Okay. So the direction of the current will be, so you can determine it from the right hand rule. Okay, second right hand rule you learned in the last class, or third. Okay, second and third is basically the same thing. Okay. So here you see that if you try to understand, if you try to connect the right hand rule here, you see that the magnetic field lines are into the screen. Okay, so that means the three fingers are into the screen. Okay, and then this is the index finger. So index finger is in this direction. Okay, now if you use your right hand, you can show that the positive charge, okay, the direction of the force is this. Okay, so the force will be in this direction, and this tells us that positive charge will move in this direction and negative charge will move in this direction. Okay, so the positive charge goes upward, negative charge goes downward. And if you remember, the direction of the current is basically the direction of uh, the movement of the positive charge. So in this case, the direction of the current will be counterclockwise, something like this. Okay, so this is the current direction. So if you consider this one, it will be opposite. Okay, so for the right hand plot, the current direction will be clockwise. Okay, that's because the direction of the magnetic field in this case is out of the page. Okay, now another thing here, you see that positive charge goes upward, negative charge goes downward. Okay, so you see that we have positive charge at the top, okay, negative charge at the bottom, and they are separated by a distance L. Okay, so because positive charge and negative charge are separated by distance L, there will be some electric field, right, that you already learned in chapter 17. Okay, so the what is then electric field? So we can determine the electric field from this equation, V equal to add. Okay, so E is V over D, and V here is the induced EMF E, and D here is L. And induced EMF here we already determined is equal to BLV. Okay, so L cancel out. So you see that electric field is equal to magnetic field times the velocity. So if you solve it for V, you see that the V is the ratio of electric field and magnetic field. Okay, all right. The next thing is some application of the induction. Okay, magnetic induction. So the first one I want to talk is the induction cooking. So in induction cooking, you use basically the magnetic induction. Okay, so let's try to understand magnetic induction, or how we cook in a magnetic induction oven. Okay, from this schematic diagram. Okay, so here you see that we have an electromagnet, okay, and a ceramic top plate. Normally these are the important component of a induction cooking. Okay, so when you connect your electromagnet to the power outlet, okay, then there will be current in the coil. Current in the coil means there is a magnetic field. Okay, so if it is just a direct current, DC current, then there will be no change in the magnetic field. Okay, so no change in the magnetic field is not useful. Okay, but you know that power outlet, the house's power outlet gives us the alternating current. Okay, alternating current means it changes its direction 60 times in 1 second. Okay, so that means the magnetic field produced in the electromagnetic coil, in the coil or around the coil, is also changing 60 times in 1 second, right? So the magnetic field changes 60 times in 1 second. So if it changes 60 times in 1 second, right? That means there is a change in magnetic field. And we already know that if there is a loop, if there is a some circuit, it can induce some EMF. Okay. Now, if we have a conducting pan, okay, for example, this, okay, so there will be some induced EMF, induced current in this conducting pan. Okay. And most of the metallic pan offers some resistance. Okay. And because of this, the current and the resistance, because of the current and resistance, the electric energy here is transformed into the thermal energy. Okay. And this thermal energy hits the pan and its content. Okay. So that's how we cook by using a induction oven. Okay. So if you just connect it with a battery, it will not work, because battery gives you DC current, and DC current means there is a magnetic field, but there is no change in magnetic field. On the other hand, if you have alternating current or AC current gives you magnetic field as well as the change in magnetic field, which can induce um, electromotive force in the cooking pan. Okay. And that's how electric energy converted to magnetic energy converted into thermal energy. Okay. All right. The next thing is the generator. Generator is very similar what you learn in the last chapter. Uh, as a, I mean, when you, I mean, in last chapter you learn about the electric motor. Okay. So generator is very similar to electric motor. Okay. In electric motor, we convert the electric energy into mechanical energy. Okay. And by using the similar thing here in generator, we can convert the mechanical energy into electrical energy. Okay. So here you can see that how it works. Okay. So it's basically simple generator. So if I turn on the water, so that means we have some mechanical energy. So you see that by using the water, we are mechanically changing the magnetic flux or magnetic field. Okay. And this change in magnetic field basically induce the current, induce some EMF in the coil. Okay. So what you need magnetic, you need a magnet. You need to change the magnetic field by, I mean, mechanically. You have to change the magnetic field mechanically, and that change will induce current. Okay. So that's basically the principle of generator. Okay. All right. The next thing we are going to learn is transformer. Okay. So a transformer is a device for increasing or decreasing an AC voltage. So here you see that it only works for AC voltage. Okay. It doesn't work with DC voltage. Okay. So sometimes we need to increase the input voltage or decrease the input voltage. Okay. So how we can do that? I mean, we can increase or decrease the voltage by using a transformer. Okay, for example, our power outlet, our household power outlet gives us 120 volt. Okay, and to charge a mobile phone, we need at the order of 10 volt. Okay, so 120 volt is too much for a mobile phone. Okay, so if you can connect directly, it will burn. Okay, so we need to reduce, and to reduce the voltage, we use a transformer. Okay, so here you see this in this example, you see that. So the power outlet, so this is a transformer. We connect the transformer with the power outlet, and the other side is connected to the mobile phone. Okay. So some other examples of the transformer you normally see around your city or close to your house are these. So these and these. Okay. So sometimes we use transformer to step down. Okay, I mean decrease the voltage, or step up to increase the voltage. Okay, most of the time we use to step down, I mean decrease the voltage. Okay. So what we have in a transformer? So transformer contains two coils. Okay. So this one we call the primary coil, this one we call the secondary coil. So here you see this is a primary coil and this is the secondary coil. Okay. Now so you see that the number of loops in the primary and secondary coils are different. Okay. So depending on the number of loops in primary or secondary coil, a transformer could be step up or step down. Okay. For example, if I want to step up, okay, we need more number here. Okay. Step up means the number of primary coil should be less than number of secondary coil. Okay. If we want to step down, so then number of primary coil will be higher than number of secondary coil. Okay, so let me show you here. Okay, so for example, if I want to step down, so here you see on the left hand side the primary voltage. Okay, and in the right hand side you see the secondary voltage, which is lower than primary voltage. So if I want to reduce the primary voltage, I mean reduce the voltage, I mean if I want to step down the voltage, you need less number of turn in the secondary loop. So here you see that. Okay, on the other hand, if you want to increase the voltage, okay, if you want to step up, okay, so here you see now the primary voltage is smaller than secondary voltage, so here we stepped up. Okay, so how we stepped up? By increasing the number of loop in the secondary coil. Okay, so that's how a transformer works. Okay, so let me go back here. So using the Faraday's law, you can show that the, okay, so let me write down the equations here. Okay, so from the Faraday's law and Lenz's law, you can show that this Vs, okay, the voltage in the secondary coil is equal to negative number of secondary coil delta phi delta T. Okay, phi B actually, right? Now this delta phi delta T is basically the same in the primary coil. So we can also write this as this minus NP delta phi B delta T. Okay, so there is only one change in the magnetic flux. Okay, that is delta phi V delta T. Okay, now if I divide one by another, I get something like this: Vs over Vp, and d phi b dt cancel out, negative negative cancel out. What we get is basically ns over np. Okay, and this equation is called the transformer equation. Okay, so if ns is higher than np, then vs will be higher than vp, and vice versa. Okay, so depending on that, we call one type of transformer as a step up. Okay, another type of transformer as a step down. Okay, so step up means secondary voltage is higher than primary voltage. Step down means secondary voltage is less than primary voltage. Okay, all right. Now if we neglect the power loss due to the coil, okay, you know the coil has some resistance, so there will be some heat dissipated by the coil. But if you neglect that, then the power in the primary coil is basically equal to the power of the secondary coil. So PS is the power in the secondary coil, and PP means the power in the primary coil. And in earlier you learned that power is equal to I, the current, and times the voltage. Okay, now if you substitute this in this equation, okay, you get for secondary coil you get IS VS, and for the primary coil you get IP VP. Okay, then if you if you simplify this little bit, you get something like this. Okay. Now, the equation, I mean, the transformer equation was something like this: Vs over Vp, Ns over Np. So if I substitute this here in this equation, we get something like this: Is Ip equal to Np Ns. Okay, and this tells us that when the voltage is higher, the current is lower. Okay, and the current is lower, voltage is higher. Okay, basically this equation tells us, and sometimes we need this equation to determine the current. Okay, so higher voltage means lower current means higher voltage. Okay, and vice versa. Okay, so let me go here. Okay, so it's a transmission line, okay, from the power plant to the home. Okay, so you see that normally at the power plant, the voltage on the left hand side, you can see that is 22 kilovolt and the current is 1 amp. Okay, and before you send it to the power line, long distance power line, you have to increase, you have to step up. Okay, in the middle you see that the voltage is 110 kilovolt. Okay, and because the power is voltage is stepped up, you see the current is stepped down. Okay, so 1 amp, from 1 amp it is now 0.2 amp. Okay, and before it goes to our home, you have to also reduce the voltage. I mean, our household cannot um, uh, I mean, if we try to connect directly to 110 kilovolt power, there will be some destruction. So we need to step down. Okay, so you see that on the right hand side, we step down to 220 volt. Okay, and before it moves to our house, we have to step down one more time. Normally our voltage, outlet power voltage is 110 volt. Okay, so you see that when the voltage is higher, the current is lower. When the voltage is lower, current is higher. Okay, so that means for a step up transformer, the current is lower. For step down transformer, okay, the current is higher. Okay, so remember this. All right, the next thing I'm going to talk is the inductance. Okay, so earlier you learn about the capacitance and the resistance. It's basically similar to that. Okay, so capacitance is the property of capacitor, resistance is the property of the resistor. Here inductance is the property of a coil or inductor. Okay, so uh, inductor is basically a coil. Okay, so normally we use okay, so this is the resistance, right? And this is the, this is the resistor and this is the capacitor. And for inductor, we use this symbol. Okay, so don't confuse resistance and inductance. Okay, so resistance is zigzag. Okay, and here it is like some kind of loop. Okay, so this is the uh, symbol for inductor or a coil or a solenoid. In a circuit, when you draw a circuit diagram, we use this symbol to represent a coil or a solenoid or an inductor. Okay, now we want to learn a little bit more about inductance and inductor. Okay, all right. So to understand this, let's say we have two coil 1 and coil 2, similar to the diagram shown in the right hand side. Okay, and let's say there is a current in the first coil. Okay, so this is the current in the first coil. So if it is a DC current, there will be magnetic field and there will be nothing. Okay, there will be no change in the magnetic field if this current is a DC current. But let's say it's not a DC current, it's a AC current. Okay, so AC current means the current changes 50-60 times in each second, and because of that the magnetic field will changes 50-60 times in each second. Okay, so what it means? It means there will be change in magnetic flux here and here also, and this magnetic flux will basically induce some EMF. Okay, now let's try to understand the EMF in the second coil. Okay, what is the induced EMF in the second coil? So the induced EMF in the second coil is proportional to basically this. Okay, and you see that this magnetic flux related to the current. Okay, if you change the current, I mean the current basically tells you whether the magnetic field is changing or not. So somehow this is proportional to the current I1. Okay, so we can therefore write E2 is equal to something like this. Okay, now if I want to write an equation, then we need a proportionality constant, and the proportionality constant here is M. Okay, and this M we call the mutual inductance. Okay, we call it mutual because it is mutual between coil 1 and coil 2, and the negative sign is again due to the Lenz's law, and you know now how Lenz's law works. Okay, so M is the mutual inductance. Okay, and what is the unit? The standard international unit for mutual inductance is Henry, and we use H to represent Henry. Okay, and from this equation you can show that 1 Henry is equal to 1 volt second per ampere. Okay, or 1 omega or 1 ohm second. Okay, you can just solve this equation for M. Okay, so M will be minus E2 delta T delta I. Okay, so this is voltage, this is second, and then current is in amp. So you see that. Okay, similarly by doing some simplification you can show that it is equal to 1 ohm second. Okay, that's basically I mean V equal to IR. You can use V equal to IR, and you can show that V over I equal to R. So that means volt over amp is equal to omega or ohm. Okay, so you substitute this here and you get this. Okay, all right. Now similar to the capacitance, mutual inductance depends on the geometrical factors. Okay, so what are the geometrical factors here that can affect the mutual inductance? That's the size, shape, number of turns, and relative position of the two coils. And also it depends on whether there is an iron core inside the coil. Okay, all right, so in a transformer we basically get mutual inductance. Okay, all right, the next thing is the self-inductance. Okay, so when we have two coil, we get mutual inductance if there is a current in one coil. But if we have only one coil and there is a current in that coil, the inductance we have is called the self-inductance. Okay, it's very similar to the mutual inductance, but we call it self-inductance because there is only one coil. Okay, and this time the self-inductance is equal, I mean is this basically. If we have only one coil, the induced EMF can be written as something like this. Not this. Okay. So here L is the self-inductance, and also the unit of self-inductance is Henry. Okay. All right. Now we can have self-inductance in a solenoid. So you see this is a picture of a solenoid. Okay, and let's say a current I is flowing through this solenoid. Okay, and the length of the solenoid is L. the cross-sectional area is A, the number of turn is N, and the self-inductance for this coil is L. I mean capital L. Yeah, don't mix with this length and this self-inductance. Okay. All right, and so cross-sectional area means this area. Okay. All right. Now, from the Faraday's law, we already know that, okay, E, the induced EMF equal to negative N delta phi V delta T. And from the equation of the self-inductance, what we just learned is this, right? Now, you can equate this because the same induced EMF are these, okay? So if you equate these two equations, you get an expression for the self-inductance in a solenoid, okay, and that is equal to L equal to N phi B delta I. Okay, so if you equate these two, you can get this one. Now, for a solenoid, we already determined in last chapter, the magnetic field is equal to this, B equal to mu 0 times the number of turns times the current divided by the length of the solenoid. Okay, now I want to know what is the magnetic flux. Okay, magnetic flux here is cosine theta. BA cosine theta. B is the magnetic field, A is the cross-sectional area, and cosine theta is the angle between the magnetic field lines and the area. So in this case, here you can see that the magnetic field is in this direction, and if this is the area, the direction of area is also this. So the cosine theta is basically equal to cosine 0 degree. So cosine 0 degree means 1. So it is basically BA. Okay, and B is equal to mu 0 N I over L times A. Okay, so if I want to know what is the delta phi B, so here you see that mu 0 is a constant, N is a constant, L is a constant, A is a constant. So you can change the magnetic flux by changing the current. Okay, so what you get is this. Okay, and this tells us that if I divide both sides by delta I get something like this, mu 0 and A over L. Now if I substitute this here in this equation, okay, we get something like this. L is equal to N and then mu 0 and A over L, and that is equal to mu 0 N square A over L. Okay, and this is the expression for the self-inductance in a solenoid or in an inductor. Okay, so all right. Now, similar to the capacitor can store energy. So it can also, inductor can also store energy. Okay, and what is the expression for the energy here, stored energy? So U is the energy here, half Li square. Okay, and it's very similar to capacitance. It was half QV, and I think one of the equation was something like this: 2C, yeah, whatever, I forgot. So yeah, okay, so here, yeah, so yeah, I think I remember. So this is CV, right? Q equal to CV. So one of the equation was half CV square. Okay, and it's very similar to this one. Okay, so you replace C by L, but here when you replace C by L, you have to replace voltage by current. Okay, so this is the equation, and for a solenoid you can replace the L that you already derived here in the last slide, and you can show that for a solenoid um, the energy is something like this. Okay, So here we did two things. We substitute L and we also substitute I. Okay, now the question is, how can I get I? So if you want to know, let's go back to the last slide. And here you see that here you see that there is a relation between B and I. Okay, so if you solve this equation for I, you get this equation. Okay, so yeah, so then simplifying these two expression, you can get this. Okay. All right. The last thing I'm going to talk is the LR circuit. And again, it's very similar to RC circuit. Okay, in a RC circuit, we have R, we have a resistor and a capacitor. Here we have a resistor and a coil or an inductor. Okay, so RL. Okay, so RC circuit is used for charging or discharging. Okay, here it is used to growth of a current or decay of a current. Okay, so so let's ignore this line for growth of a current. Okay, so when your switch is connected here, what we get is the growth of a current. Okay, and the growth of a current, you will see something like this. The current grows exponentially, very similar to the charge growth or charging exponentially in the RC circuit. Okay, you can see that here. Okay, so here you see we have a resistor on the left hand side and then an inductor. Okay, so this is a resistor, this is an inductor, this is a current probe. Okay, basically we want the current. So here we have also voltage. So in fact, we are not interested on voltage in this case. Okay, so I want to show you how the current grows. Okay, it will grow exponentially, very similar to the charging in RC circuit. Okay, so you see that the current is growing. Okay, and similar to the charging, you can show that the growth of a current is this: I equal to I0 and 1 minus e to the power minus t over tau. Okay, so here tau is the the time constant, and this time constant is not equal to RC because here we don't have C. Okay, do not confuse RC of RC circuit and L over R in a LR circuit. Okay, so this is the time constant, and I0 is the maximum current. Maximum current here is equal to you can determine it's from the Ohm's law, and that is equal to V0 over R, or you can say that the EMF, the battery EMF over R. Okay, all right, now what is the significance of the time constant? So when T equal to time constant or equal to L over R, then the current grows to 63% of its maximum current. So you see that at time, when time equal to time constant or one time constant, then it grows to this much, that is equal to 63% of the maximum current. Okay, and similarly you can show that when it is connected. Now if you ignore this part, okay, and close this switch, there will be decay of current, and the decay of current will be something like this. Okay, and the explanation is very similar to the discharging. Okay, all right, so that's it for this chapter. In the next lecture, I am going to solve some of the classwork problem. All right.